I'm Kristian Hovde Liland. I'm from Norway, from Norwegian University of Life Sciences. And I'm going to talk about encoder-decoder networks. So basically autoencoders with some added flavors. So thank you for giving me a starting point here. Let's see now. Yes. Oh, yeah. Okay, so you've already seen the autoencoders and their structure. I've stolen my figures from Wikimedia, so they should be okay, I think. Yeah, so I'll be talking a little bit about the autoencoders and their generalizations, some overlap, some other stuff that we've seen before, and 3 different applications. None of them are purely NIR, but they are all in chemometrics and spectral domain. So I'll talk about the deep scattering autoencoders for complex pre-processing, a little bit about spectral predictions in hydrolysis monitoring, and then constituent predictions with physics-based decoders. This is farthest away from my field, but it's interesting. And then a little bit of wrap-up and future perspectives. So first, some history. So I think it's a little bit disputed where we have the actual origins of this. But at least Hinton and his posse, they had this backpropagation without a teacher in 1986 that started some of this. And you also have Kramer from 1991-92 with his auto-associative neural networks. So as Federico said, we're associating an input with an output, and they should recreate each other. So we should, in our case, put in spectra here and hope to retrieve the spectra at the other end. Yes. So we have the 2 basic building blocks here, the encoder part, which is the first side here, which takes the spectrum and does some operations to it. I'll come back to different things that can be done to this. But basically, it's a neural network that restricts down to a few nodes in the middle here, which has different names. In this case, we call it the code, but it's the underlying patterns that we're looking for in the data. So it's just a function. So this hidden thing in the middle is a function of the input. And then we have the decoder, the nonlinear reconstruction of the original data that takes the code as input, so the hidden part in the middle, and a function of that to try to recreate everything again. So these have very specific roles. The first one trying to find the patterns, the second one trying to recreate structure to put the patterns back in to again. So in general, we have a combined function where the output is a double function of the input. That's the one that we're optimizing in a way with our system here. So as Fede already mentioned, we have 2 basic types of these with the multi-layer perceptron setup, where we have these dense layers, so just matrix multiplication and some kind of activation function on top of that, typically the ReLU function or some other more or less exotic way of trying to induce nonlinearity into this. And then the reverse operations here, just expanding the same thing again to full size. And then we have the convolutional part that you also mentioned, where we have convolutional layers, and either there is the pooling operation, or you could do this, what's it called? When you have not single steps in our convolutions, but we jump over some so that we reduce the size just by not covering every single possible position of the convolution filters. Right. Strides, thanks. And then we have some kind of either deconvolutions, which is the opposite operation, or we can have other types of operations that expand this. So some kind of opposite filter. So one of the variations that was not covered was the variational autoencoders. This is a different, it's related in a way to the GANs that were mentioned, but this is a little bit different. So here we have also an encoder and a decoder, but in the middle here we have a latent space, which is explicitly formed to have some distributional properties. So we're not projecting onto a single point in space, we're projecting onto a distribution. And this also gives us some other possibilities. because we can now use this to generate new data if we want to. So then we can input some kind of random noise into these distributions, and from that get fresh spectra at the other end. And then, like Peder said, also we have this generative adversarial network, or GANs. And as I said, we have this one network that generates something from noise, and then we have the other network that tries to discriminate between the real data and the noise. And these have a competition where we're hopefully getting better and better images or spectra or whatever we need, and also a better and better discrimination between these. And the examples of the naturalness and accuracies of these is just mind-blowing. You get, if you're using this for generating pictures, for instance, you have photorealistic faces that do not exist in real life, but that look really convincing in a way. Also used in generating spectral data. I had a master student working on variational autoencoders last spring. That project wasn't super successful, but that's mostly because he made some early choices in the wrong direction and stuck to those, whatever we said. So I've seen better applications of this, because it's often very interesting to get more data out of the little data that we have time and money to gather. So yeah, but when I used the term encoder-decoder, I think of that as a more general thing than the autoencoder. So X this X is no longer a direct reconstruction. We're not trying to find the exact same underlying spectrum that we had. So instead, we could have some kind of function that we try to mimic. So here, our input spectrum is it's subjected to some kind of complicated function that might be time-consuming to compute, or there could be some underlying reason why we don't want to do this operation too often. And then the autoencoder could try to generalize this and take a shortcut in a way. So referring to Harald Martin's work, I would think of this as kind of a meta model that takes a shortcut, but still now in a non-linear way, but it's avoiding a lot of the complicated things. And I'll come back to an example of this later. We could also add more parameters into the function. So one of the examples will be a time delay. So then we have input spectra coming at one time point, and we'll be predicting output spectra at another time point during a chemical process. So that's another generalization. And then this decoder could, for instance, be some kind of not a neural network per se, as we know it from these simpler ones, but it could be based on some kind of underlying physics-based model. So some first principles or general knowledge about how to reconstruct spectra. So that's the last example I'll be going to. So the first main example here. Here we have infrared spectroscopy of cells and tissues. They may be affected by Mie scattering. I think maybe Achim will come back to this a little bit in his talk. And this results in heavily distorted spectra. Typically, we can use a method called Mie extinction extended multiplicative signal correction, NIR. That's like a state-of-the-art alternative for trying to correct these. It's based on, from my side, intricate Mie theory. I'm not very into the physics about this. And just a screenshot from one of the articles. There's a lot of operations going here, a lot of special knowledge about how waves propagate and how things work in here. And there's an iterative loop. And this is very time consuming. Oops. Wow, that's a bit old.
It always keeps you on the edge.
Yes, of my choice. Okay, so an iterative algorithm, relatively high computational cost. And it's dependent on which reference spectra, which data you put in. You can use that model again for those data, but there are some limitations to generalizations. Then comes the descattering autoencoders. So we have this article from 2020, Deep Convolutional Neural Networks recovers pure absorbance spectra from highly scattered distorted spectral sets. So this is the main setup. So we have the true and tested EMSC path going from the raw spectra to the corrected spectra. We are inputting and using our physical knowledge, and this takes quite some time. And then we set up a encoder-decoder that goes directly from the raw spectra to the corrected spectra and mimics the whole operation. So we need still the MEMSC on to create training data for this, but this can be used then very quickly afterwards. And the point here is that we have this kind of structure. In this case, it's a convolutional based one. So we have some convolutional layers. We have some batch normalization, which is typically used together with convolutions. We have some pooling in this case. And then we have our inverse convolutions, or deconvolutions as they're also called. So from our input spectra with a lot of knee scattering, and then to the output spectra that are cleaned in a way from this phenomenon. So the whole point, we are mimicking the MEMSC with this simple one. Good things about this is that we can combine sets of corrections that are based on different reference spectra. We can pool data from several sources into the same autoencoder and train them all together. So it's a kind of a reference-free approach in a way. It has a very nice regularizing effect on noise. So we see that the spectra that we get out of this are often cleaner than the ones that were done by the original MEMSC. And the big thing here, we see more than 3 orders of magnitude faster corrections when this has been finished and trained. So we can leverage GPUs because we're using like TensorFlow or PyTorch or these good frameworks that use all the resources that we have. So for instance, here, if you have an image of 200 by 200 IR spectra, putting in MEMSC takes around 3 hours to correct one single image. And using this encoder-decoder, we're down to around 8 seconds. So instead of putting it on overnight for a couple of images, we can then do many images while we're drinking coffee and coming back. That's good. So the second example here. So we are doing some monitoring of processes. Sometimes it can be interesting to get some feeling on how will the spectra look at a future time point. In this case, we are looking at enzymatic protein hydrolysis. So we have some rest raw materials from some kind of production. I look mostly at poultry slaughterhouse data where we put this into a tank with some enzymes and heating and stirring around. And this goes on for a period of time. And then we take FTIR measurements during this process. And the nice thing here for the processing plant would be to know early in the process, how will this work? How will this particular mix of raw materials end up after some time? So how much will the yield be, for instance? When should we stop the process? Should we adjust something? So for instance, the amount of water, the temperature, or should we do something to the enzyme composition here to get an optimal end product? So enzymatic protein hydrolysis of rest raw materials. We want to use this for process control and end product categorization. If we can say at the beginning of a batch that this is going to go to human consumption, or if this is going to animal feed because it's a low-grade end product, that would be a nice thing. And rapid feedback could improve the quality or increase the yield if we can do this in a rapid way. So we have a publication from 2022, which is called Encoder-Decoder Neural Networks for Predicting Future FTIR Spectra, Application of to enzymatic protein hydrolysis. So it's a cooperation with Universidade in Oslo. You might recognize the basic structure. We have our input, we have our output, We have a lot of convolutions going on. It's the same basic thing. But on top of this, we now extend this with a little bit of MLP on top of here. So we have multi-layer perceptron, which takes in time as a factor into this. So that means that our input spectrum here will be at one time point. Then we have a time delta coming into the model, and we get our output at a later point in the process. And when we train this on many time points in this process, it turns out we get actually very good predictions of how the whole spectrum will change during the process. Or we can do this for a single input like the top one here, but we can also have multiple inputs, which makes this a little bit more robust. So let's say that we take samples at time point 1 minute, and 5 minutes and 10 minutes, and then we combine those in here as inputs, and also time delta related to these, and then predict what happens at a later time point. So that's gets more robust because we get also the trends into the whole thing from the different spectral time points. This works very well. So we can use this for peak quantification if that's what we want, or we can put this further into a model that tries to predict some kind of output. What we've mainly done is to look at average molecular weight. So just how does the whole product break down? How will the proteins and peptides change molecular weight because of the enzyme breakdowns that are happening in the process? So then we add a simple linear model, so a PLS model on top of this, and use the future spectra as inputs to that to say what is the average molecular weight of our samples, which works pretty well. We are not exactly at the level of accuracy that we would be from having the actual samples at that time point, but it's good enough for doing basic changing of the processes as we go. And then the last example here, physics-based decoder. This is from a doctoral thesis that I was an external examiner of. So this is the one that I have no hands-on experience with, but which I am inspired by, and I'm trying to use in my own research too. So in this case, we're looking at simulations of spectra from fundamental properties. So that's possible for some types of spectroscopic techniques. In this special case, it's X-ray fluorescence, which is the underlying principle here. Then you can make a model based on photon counts, continuum scales, energy probabilities and transitions and all of this to use input elements to recreate a spectrum to some degree.
That's Match-Dirks.
Yeah, that's theirs. So of course you could do this for a lot of different spectroscopic techniques. You just need to know the principles. Or you need a good machine learning method that can mimic the same thing. Yeah, so input amount of each element, and then some background signal parameter here to control other things outside of the actual signal. Yeah, so he had this paper, Dirks and Poole, Auto-Encoder neural networks incorporating X-ray fluorescence fundamental parameters with machine learning. And you might see the same structure here with an encoder-decoder. So the encoder is just like we've seen with the other example. We have convolutions, we have some connections. In this case, it's a combination of an MLP and convolutions. So it's very similar actually to what Tom Kern showed. So some layers of dense things after a convolution. And that's also what I've seen with my PhD student, Runa Helin, that combination is very beneficial. It's very simple to have a single convolution and then just to extract features and then let the MLPs do the rest. In this case, the hidden layer in the middle, or the code as it was called in this case, or the underlying properties, will now be the actual elements that we're looking at, plus some extra parameters to control the spectral variations around the element variation. And then comes this simulation machine here. And it's been built using equation in such a way that the whole thing is differentiable, so that you can get your weights propagated and your signal propagated back again here using back propagation through every single step of this simulation. That makes it highly integrated, and you can optimize the whole thing in one big chunk instead of having to first optimize this, for instance, and then optimize this as a based on the output. Let's see. Yeah, fully differentiable, as I said. And what we get in practice, or what he gets in practice from this, are improved predictions, because the sensitivity of what we see inside here, if you only use this part to predict our outputs, is quite low for some elements. But if you can include the whole output spectrum in the loss function, you improve the whole sensitivity business quite a lot. And that's exactly what I want to use in some other applications that I'm working on. So we see that if you try to then later predict these ones, the accuracy is improved. Not so much for the very simple ones, but for the ones that have low concentrations, or that are not giving too well or too much signal in the X-ray, that are borderline for that. They are the ones that gain most from this strategy. Yeah, I see I'm very much on time. Okay, so we've seen encoder-decoder structures in neural networks. They open up to some nice possibilities. We can get quicker, more robust pre-processing in cases that are more complicated. I also have, I mentioned Kristian Liland, he has a separate paper where we are looking at only pre-processing using neural networks, comparing it to traditional methods. And the experience is that neural networks, they do whatever they want to. You have to be very strict on them to actually force them to do what you want them to. So if you try to make one layer that is a pure pre-processing layer, and then the rest should be your prediction machine in a way, it mixes it up completely. It does whatever it wants just to have the perfect relation between your input and your output. Several different architectures we've tried, we have to force to a maximum to actually make it do what we want it to. Which is good and bad. It's bad because it's harder to interpret and harder to distinguish between the different roles of things. Good because it takes responsibility and does exactly what it's told to do in a way. Prediction of future spectrum. I find it fascinating. Short as that. And then this improved prediction modeling. This is seen a lot now in the image domain too, that people are adding recreation of the original images as part of the pipeline, in addition to some kind of prediction engine, be it a regression or a classification, or also the semantic segmentation, where you try to do a pixel-wise segmentation of your images, still having that pipeline out to recreating your original data. It gives you this connection between the original data and the properties of the image that would otherwise maybe be lost in the process of doing the predictions. So it has this regularizing effect, which seems to be beneficial in many cases. So we're also trying to put that into other kinds, not just X-ray, but into medical imaging to see if we can force the networks to use more power on recreation in the process. Yeah, combined with predictive models, encoder-decoders enable leveraging unlabeled data. That's maybe something I didn't mention too much. And now, of course, I can't recreate whatever I did to find this overview. But the point is that you don't have to always put label data into the process. You can also use it just for input to output, even though you have your elements in the middle, for instance. You can also just put in unlabeled data, send it through to strengthen the patterns, to find all these local variations in your data set. And then you have some of the data with labels, and then you just activate and deactivate the loss functions that you need. And then you have this nice combination where you can have lots of data, cheap data, because labeling is usually the most expensive part of this. That's a nice added feature. Yeah. And then I use Google Translate.
We have time for a bunch of questions because if you check the time schedule, I made a mistake. There was half an hour missing, so I was somehow accounting for what happened. So,
Okay.
yeah. So please, Martin.
This future prediction, it's really nice to have the spectrum because then you can apply all the method you have for that. But it would be valid to compare with not going via doing the spectrum, just do the prediction immediately. Is this as good, or does it cost something extra to do it via the spectrum, so to say?
Yeah, we haven't done exact comparisons of those two. That's something we had in like the future perspectives in the paper. Yeah, so I think the cost of doing the actual modeling here is quite low, but you might be adding some.
I'm thinking accuracy. If it costs on accuracy to go this detour, I mean that detour is really nice to get the spectra, but if the cost is too high, or maybe
you might get some other artifacts if this is a bad model, of course. So I can't guarantee it for all applications. But this, the possibility of using any kind of method on the output is intriguing.
Can I make a quick comment? I was very interested in the bit where you were making the features both recreate original data and do predict. That's, of course, is exactly what PLS.
Yeah, I actually have some notes that I can't see on my screen here where I mentioned PLS because exactly this, I compare it like if you have CCA or RDA, these methods that are very hungry on the response side, but you don't get the recreation of your X. It's exactly the same thing here. We are regularizing by recreating the input. So, yeah.
Yeah, there was a question here.
So thank you for the presentation. Very interesting. I'm just curious about when you spoke about the spectral prediction for the new times coins. Just to keep understood, you have the encoder and decoder, and the middle we have the bottleneck, which is NLP, right? And it takes the feature from the last layer of the encoder, and then on top of it, you are assigning
Yeah, so if it's talking about, so we have our input spectra from one time point, and then we have a time delta. So it's a single scalar that we add to this, and then that one is added right after the bottleneck. As soon as we start our decoding, it's input step. Yeah.
Okay, thank you. Also, I'd like to know how many cycles did you use to create an autoencoder like that?
In this particular case, the full sample count is 885, but due to replicates, I think the actual count is 232. However, this is a very heterogeneous data set with fish samples of two types, and we have poultry of chicken and turkey. So there are some nonlinearities and some actually some what's it called, reference analysis aspects that are not taken 100% into account. So it's a complicated data set.
And one last question, I would like to know if you added any special treatments before feeding suspecting to the net, like scaling between German one, mean, and deviation. Yeah,
so we typically do the classical pre-processings that we do in other chemometric cases, but scaling is often useful. Ordinary auto-scaling typically gives a good starting point, or just like dividing by the maximum value of the whole data set to get it into a range. It doesn't matter if you have a lot of resources and a lot of time, because typically the weights will be found and the model will be good over time anyway.
Yes.
But to make this fit to the initial weights that are randomized with normal random or normal distribution and cutoffs, then it's just faster if you have them in a range.
How,
Just a question, you mentioned the batch normalization. What's the purpose of that?
So batch normalization is a technique that when you put data into your networks, you do it either one sample or a few samples at a time. And that little, that's the batch in a way.
Okay.
So you're subtracting the mean, dividing by the standard deviation for every single channel at that layer, and then you're learning new standard deviations and means. So it helps with outlying samples in a way, or high variation to get into a common framework.
So then follow up, is that related to SMD and so on? It's just that you do it on a set of spectra instead of each spectrum separately?
Well, yeah, it has an analogy to that, but it's inside a network, and it could be just before the final layer. So it's more a regularizing technique inside.
Because the reason why I ask is that I see the neural net as a general Taylor expansion, and most of the elements in a neural net are additive. I'm not an expert on neural nets, so someone must teach me here. The main thing I want to get out of this meeting and go home with is a comforting statement saying that the neural nets that you are using can handle both additive and multiplicative effects very nicely, like the MSC. And I would hate to go home with the notion that you can't do it, and you actually approximate a multiplication with an addition, which is the Taylor expansion of the product is a sum. It's a horribly bad approximation. I'll come back to that in my lecture. So please tell me that you can handle both additive and multiplicative effects in each spectrum, like an EMSC inside the neural net. Please tell me that.
Well, there was a mention of what's it called? Federico, it's a general function approximation.
Yeah.
Yeah, universal approximation. Yeah. So given that you have infinite number of nodes, so yeah,
That's not science.
but in theory it can recreate whatever we put in. So
Yeah, but the infinite compute, that's not science.
no.
And it's certainly not explainable there.
No.
So we are humans.
No, I mean, neural nets at this point, depending how you look at them, you have two choices. You use them all as as a black box, and if it works, it works. It's good for your application. You don't need to know why. That's industry usually like. And then you have chemometric and chemists that like to see where the information comes from, and to see if theoretical models match what they're supposed to do. That was one of the messages from the Innsbruck NIR meeting, is that there would be no model without explanation and no explanation without model, or something like that, right? So for neural nets, there are a bunch of techniques that allow us to explain what the neural net is doing. We don't know if they're doing the right thing that we expect them to do. That's a different thing. Okay, we can probe them to see which features they're using to make the decisions they're doing. But sometimes those decisions, those features, doesn't correspond to any of our second order vibrational state that we were expecting. Okay, so on that point, there's still a lot of work to do. So to answer your question, you can train a neural network to separate scattering to separate the scattering part from your model, from your spectrum. If you understand how that is doing it, that's a bit different. Because this is one of the things I want to bring to the discussion later on, is that most of the neural network stuff that has been doing chemometrics has been done by chemists or by physicists, right? There aren't computer science departments investing time usually on chemometrics. So NIR spectra or 1D spectra, it's low sample database, it's not that interesting like images for vision or NLP. You don't have this big data set, so you don't have an active development of an architecture specialized for spectrum. Okay, that's one thing. What we do here is we use patches from natural language processing and from computer vision, and we adapted to 1D. And they work fine, right? But they were not developed to deal with NIR spectra. And that's one of the things that I would like to push forward. I mean, to try to get together with computer science departments and look at what priors can we bring to the network, to the architecture, in order to make it better analyzing spectra. We're still a long way from it, okay? That's one of the things that I would like to convey in this workshop, is especially that. But I will leave that for the discussion later on. Okay. I have a question if I.
Yeah, just a comment on we also made an EMSC layer as the first layer in one of the networks, and worked well. But the spectra that we get out of the like the reference spectra that it creates have nothing to do with the data. They look like random noise. So so the model does whatever it does. It doesn't. We could force some kind of multiplicative effect into the model, but it would probably just skip it and do something that is easier for it to recreate the same effect, but we wouldn't see it because it would be hidden in the combination of parameters.
Yeah, on that aspect, you can craft a layer and make it non-trainable. Like you prefix your weights. So gradient descent on backpropagation doesn't affect that layer. So it gets fixed. But that means that you have to craft by hand the features you want to see, right?
Yeah.
So basically that's just doing pre-processing in the beginning.
Yeah, you can just split it out and do it before the network.
Yeah. One of the things that I want to ask you is that you used variation auto-encoders, right? Have you tried or experiment with not variation auto-encoders, but conditional variation auto-encoders? Which means that your encoder creates this distribution from which you can sample from in the bottleneck, but then you condition it by providing your input value. For example, some regression value that you want to.
That's exactly what my master student did. Actually, he had this CT-GAN and CT-VAE, so conditional table based. So it has some properties that are not good for our type of data. But he used the conditional ones and tried to also include the response as part of the spectral generation.
Okay.
And he trained them for many epochs, and there were, a little bit of a signal in there, but extremely noisy output spectra. So he needed to do some after processing to get them to look like actual NIR spectra. So it's not a great success, but there is a lot in there that could be developed.
Okay. And do you see any difference when you do the auto-encoders using just fully connected layers or neural convolution layers with pooling? Do you see which one works better?
Well, I use most of the convolutionals with shards actually in my and I think that's probably what's being used here in this paper, because I made the base models and then took over my code and continued the process. I'm not exactly sure about that, which is best, but my notion is that this combination of one convolution plus dense layers works well when you have spectral data. My doctoral student had a lot of different architectures that he tested. Reproducibility is pain in somewhere, but
Just one final question. TensorFlow Python.
Yes, please.
Which one? TensorFlow.
I've always used TensorFlow, but that's because I'm an old man.
No.
Now all my students use PyTorch, and my next project I will try to converge.
Yeah, let's say one more thing. Oh, there's nothing else.
I want just to ask things I do not understand. I mean, I don't understand many, but an old one. When you have a pooling layer, how you decode the pooling? Because, for instance, if you use a max pool out of maybe 4 numbers, you only pick 1. Then, when you expand it back in the decoding, what you put for the neighbors, you repeat the same number.
So are you thinking in like the back propagation part when you are putting your
The upscaling of the decoder.
I mean, because
Oh, yeah.
I understand that if you have a filter,
Hmm.
then you have an inverse filter.
Yeah.
So you can do the filtering and the unfiltering. But when you have an operation that compress,
Yeah.
which are like an average of taking the maximum, then how you
So it would be
you go expand
it
that.
would be possible to use like an unpooling in a way where we just copy the maximum value and or copy the value onto several. That's one of the simplest techniques. Some also use more like this Lanczos bidiagonalization for expanding, so proper old image techniques. But then the deconvolutions is maybe the most used now, especially if you have this semantic segmentation where you are reliant on having the expansion, where you have an opposite convolution operator. So you can show it. I can't explain exactly how it happens, but I have a slide. So.
And then I have a second question. How much the weights can change from the original? Because I mean, Federico shows some filter that have some meaning in terms of kind of feature they extract. So during the learning process, this number will change.
Yeah.
And how much they change? I mean, will they become something that can be completely different? So if I have something that in the beginning I select because it's doing, I don't know, let's say smoothing, can in the end this instead change so much as can become an high-pass filter, or it will change smoothly during the learning?
My experience so far is it changes a lot. So if let's say that you have a single convolutional layer in the beginning and you have 8 filters, you will not see the same filters again when you run your model from scratch, because everything is initiated randomly, and it's the combination of all the filters that does the job. So everything, all the paths that are used through the network, they can be recreated in different ways. So yeah, I haven't seen much reproducibility within the network, but the performance from going from the input to the output can be very similar from time to time. So,
You can reproduce the results. When you initialize your weights, you just use a fixed random seed. And every time you run your model, you initialize your network the same way.
And you get stuck in the same local minimum.
You can get that.
So typically we run them and then we show like a confidence interval on predictions at least to get some average in there.
Okay, one last question.
My mind goes a little bit to applications with some interesting things that you shared about some examples. When you showed the examples that correct for the linear scattering, my mind goes to the other problems, for example, the issue of the spectra and producing spectra and normalizing or standardizing for all the issues that come from different instruments, people measuring differently, different temperatures, and all a bunch of other metadata perhaps, if correctly labeled in the spectra, will have a problem like this. Any experimentation, any experiment that you've done with that, any interesting applications you've seen with that?
Yeah, we started briefly with my doctoral student before I had to go on to the next position with making a combined neural network that would take several different types of, let's say, NIR data with different spectral ranges and from different instruments, different responses to make like a global model across all of this, and then have some additional parameters that would make it help it through the process. But he never had time to get this upscale and test the real performance of this. But making things robust across everything, of course, would be a holy grail.
I have another application that is interesting, or reminds us of another one. You showed also the encoder-decoder for predicting future FBIR spectra. Another interesting problem is food is mostly additive processes where we get ingredients together and do consequentially end up with a product that ends up on a plate. As you eat a raw chicken or a piece of chicken, and even that can be deconstructed. We're already seeing that in other processes for alternative proteins as well. Anyway, my idea is any interesting applications, any interesting experimentation around predicting, instead of time, predicting different components and ultimately resultant spectra for.
Yeah, that's an interesting. So you're actually several sources and then another. Yeah, I haven't seen that.
The simplest form would might be in one that is fairly standardized, is ingredient, the food ingredients business, where you might have individual ingredients that have actually been even isolated, but whey protein isolates and different types of ingredients.
Yeah.
But you might go to more complex things where you have more or less, let's say, less pure ingredients, and that is even interesting.
Yeah. So then the recipe is still additive, but I guess on a molecular level, you will have recombinations of things that makes it.
Yeah.
You need something non-linear. Yeah.
And ultimately, all of that is knowledge that is available to us. Again, going back to your example, all of that domain knowledge is available.
Okay, let's take the speaker again.